Okay, guys. Today we're just going to finish going through the last of the questions from the example paper that we worked through. We were on to question 13. Last time, if you remember during the live lesson, we went through the one about using those smartwatches to measure somebody's pulse by a light emitting diode and a light dependent resistor. So today we're on to a different one. On to question 13, which is still kind of physicsy but electricity. So let's give it a gander. Now, as always, this will be much easier if you've got your own papers in front of you, and just check off the answers you got against what I've come up with and see if there's any way you can improve on your work card. Here we go. So question 13, electrical energy is one of the most important types of energy that we use in our daily lives. An electrical appliance has a power rating which tells you how much electricity it uses. The table below shows the power rating of some common household appliances and the forms of energy that are produced in the appliances. Here's the table. Okay, so what have we got? We've got the appliance, like the name of the device, its power rating in watts, the forms of energy that it produces, and the current that it draws from the power grid in amps. Which appliance listed in the table uses the most electrical energy? Well, they say that the power rating tells you how much electricity it uses, so we're looking for the one with the biggest power rating, which is the dishwasher. The dishwasher, because it has 2,300 watts. But even if you got confused and you went by current, it also draws the most current, so that would work as well. Select one of the appliances from the table above and name a useful form of energy produced when the appliance is being used. Okay, let's think about the coffee maker. If you're making coffee, you want it to be hot, so you want the heat. So heat is what you would want in the coffee maker. So if I chose the coffee maker, the useful type of energy would be heat. We'll do the others, we may as well. If I chose the TV, the useful ones here are light and sound. The light that the screen gives out and the sound so that you can hear the screen, hear what's going on. Heat is not a desired product here. You don't want your TV to get hot. It does, but you don't want it to. So the TV useful form of energy could be either light or sound. Kitchen blender. Okay, so you've got three types of energy: heat, kinetic, and sound. They're noisy. You don't want them to be noisy. They generate heat. You don't want that. What you want is the kinetic energy. You want the blades to move. So for the blender, it's kinetic. I need to be a little bit neater, I think, as we go on. And the final one, dishwasher. This time, you want heat because you want it to works better with warm water, and you want kinetic because you want the water to be moving around. You don't want sound. So any one of heat or kinetic will do the job there. For the appliance you selected, name an unwanted form of energy produced. Okay, well, for the coffee maker, that's sound. For the TV, it's heat. For the blender, it's sound or heat. And for the dishwasher, it's sound. For the appliance you selected, here we go, a little bit trickier now. Calculate the voltage applied across the appliance and include the unit for your answer. Okay, well, let's think about what numbers we're given. We're given the power rating. And if you remember, power is equal to current times the voltage. So we'll use their symbols. We say power in watts is equal to the current, which they give as an A. And let's just stick with V for voltage. And they want us to find the voltage for one of the appliances. So it doesn't matter which one we choose. Let's go with the dishwasher. That might give us a nice easy number to work with. So if the power is current times voltage, you need to do a little bit of algebra here. We're looking for the voltage. So we need just to get voltage on one side. So what I can do here is if I divide both sides of this equation by the current, I can get rid of it from the one side. You might have learned it as like bringing it across the equal sign, where if it's multiplied by one side, it's divided by the other. Both are the same thing. So basically it ends up with W over A is equal to V. Just to recap what I did there, I've either divided both sides by A, which will cancel out on this side, and divide this side by A, or if you think about it as bringing it over, that works too. So power divided by current is equal to voltage. I'm going to go with the dishwasher with a power rating of 2,300 watts and a current of 10 amps. It has a voltage of 230 volts. Okay, now you could have done it with any of them. In fact, let's just do one more. Let's do the TV, just for the sake of argument. TV draws a power of 115 watts, so the current of 0.5 amps. So this time it would be 105 watts divided by 0.5 amps, which would also give us 230 volts. So all of these will give us 230 volts because that's the voltage of mains electricity that comes through the wall. Okay, what pattern, if any, exists between the power rating of the appliance and the current? Okay, let's look at the data. We've got power rating here and current here. So let's look for the smallest power rating and see how that relates to current. The smallest power rating is the TV, and that draws a current of 0.5. The interesting here is the smallest power rating is also the smallest current rating. All right, let's jump up a level. The next smallest is a kitchen blender with a power rating of 345, and its current it draws is 1.5. And you might see the pattern starting to emerge now. So let's go up another level with the coffee maker drawing 1,380 watts. That's third in the list of current, third highest in current as well. So our pattern here is that as the power rating increases, so does the current. So as the power rating of the appliance increases, the current used also increases. You might know as well that's a positive correlation, is the name for that type of relationship. Okay, let's keep cracking on. Sustainability issues arise from the generation and consumption of electricity. What do you understand by the term sustainability? Well, sustainability refers to how much of the Earth's resources we use and whether we can sustain that use as a species indefinitely. So it's whether we can use something in future, like how ecologically sound the use of something is. There's loads of different ways we can phrase this. Let's go with whether we can continue to use that resource, in this case electricity, or the different ways of generating it. So just one way in which we can reduce how much electrical energy we can use. Okay, well we could turn off the lights more. So turn off lights when you're not in the room. That would be one way. The biggest one I can think of is, most devices, when you turn them off, they're not really fully off. They're in standby mode. If your electrical appliance still has a little red light on it or green light, it's still drawing a lot of power. So fully powered off appliances is another one. And there's a load of other ones as well, just for using less electricity, like we could use the dishwasher on a lower setting or the washing machine on a lower setting, more ecologically friendly, or use them less often. All of those are good options. Okay, electrical energy can be produced using renewable and non-renewable sources. Identify 2 renewable sources of energy from the list below by placing a tick in each of the correct boxes. Okay, well, non-renewable means that once it's gone, it's gone. Renewable means we can use it again and again and again, so that's not going to run out. So, for example, the oil on the planet will run out, whereas the solar energy we can get won't. The sun's always going to be there, so solar is renewable. At the same time, natural gas will run out, but the wind isn't going to stop blowing, so the wind is the renewable one there. There's our 2 ticks, like they've asked us to do in the boxes. Bob is your uncle for question 13. Okay, question 14 is a little trickier. They get more difficult as we go on. So the ones at the end of the test tend to be a little bit more difficult than the ones at the start. That's kind of designed that way. Okay, so question 14. Read the article below, adapted from an Irish newspaper, and answer the questions that follow. All right, I may as well read through it while we're on here. UCC study on high fibre foods ease stress effects. Interest has been growing in recent years in the link between gut bacteria and stress-related disorders. Researchers at University College Cork, UCC, have shown that the microorganisms in the gut, or your intestines, are really important for our brain health. Bacteria in the gut produce fatty acids, which are a source of nutrition for cells in this part of the body. Foods such as grains and vegetables contain high levels of fibre and will stimulate gut bacteria to produce these fatty acids. The UCC study involved feeding mice the fatty acids normally produced by gut bacteria and then subjecting them to stress. Using behavioural tests, the mice were assessed for this anxiety and depressive-like behaviour. The researchers found that there was a decreased level of this type of behaviour when fatty acids were consumed. These results provide new insights into mechanisms related to the impact of gut bacteria on our brains and behaviour. Okay, name a type of food that is high in fibre. Now they do mention some in here, so foods such as grains and vegetables. So grains and vegetables. The study involved feeding mice fatty acids and then subjecting them to stress. Describe a control experiment which the students could have used in this investigation. Well, the control experiment is to make sure that whatever thing you observe is because of what you're observing. So what I mean is, you want to make sure that we saw here that these mice were less stressed. We need to be sure that that's because they were getting more of this fibre and causing more of these fatty acids. So I suggest a control here will be you could use a group of mice, and this time you could not feed them the fatty acids. So use a group of mice that are not fed the fatty acids. and subject them to the same stress that the mice in the original experiment were subjected to, and subject them to stress 2. Now, of course, if you just let the experiment there, there'd be no point. If you're just stressing out mice to be mean, we have to see what effect it has on their behaviour. So then measure their behaviour and see if there's a difference. Let's see if it's different from the original group. I'm running out of room, so I'm just going to say changed. What observation did the scientists note about the behaviour of the mice after they'd been fed fatty acids? Okay, we'll just scan through it. They had decreased levels of stress and anxiety. So they had decreased levels of stress. Do you agree or disagree with the use of animals such as mice in scientific research? Explain your answer. Now this is kind of subjective. You might have different opinions from each other. So some people might agree because they could say that, well, if these things are tested on animals, we can know they're safe before we test them on people. That's one argument in favour of it. An argument against it might be that you think it's cruel that these are tested on animals and it shouldn't happen. So both of these are viable options. You just have to explain why. So you can't just say yes or no, you have to say why. Okay, let's keep cracking on. Human health is affected by environmental factors such as stress. Name another environmental factor which has an effect on human health. Well, you could say air quality. You could say how much food they got growing up. You could say environmental factor. You could say how much sunlight they had access to. You could say how much water, fresh drinking water. It's basically anything outside in the environment that has an effect on human health. So water quality, food quality, even access to good sleeping habits and being able to sleep properly. All of these are viable options. The article highlights a beneficial role of microorganisms in human health. State another example of how bacteria could have an effect on human health. So we've talked about a beneficial role, about how they can be useful. They can also be very harmful. Bacteria can cause infections, especially if they get into an open wound or into a part of your body that they're not meant to be. Bacteria can cause infections. The image shows bacterial cells dividing in order to reproduce. This is an example of asexual reproduction. Describe one difference between sexual and asexual reproduction. Well, in sexual reproduction, you need a male and a female. In asexual reproduction, it's just the one thing that's going to split. You don't need the two parents. So that would be one big difference. Sexual reproduction requires two parents, mom and dad. Asexual reproduction requires only one. So another difference is with sexual reproduction, like what we do, like what mammals and people do, the offspring is more varied and different from each other. In asexual reproduction, they're going to be much more similar. In the case of these, they're going to be exactly the same. So you get an increased diversity in sexual reproduction than you do in asexual, less diversity. And for the species, that is good to have as much diversity as possible, because if a disease arrives that wipes out 90% of people, the 10 that survive will be able to pass on their useful genes. Having a varied amount of genetic information floating around makes the species more resilient and more difficult to destroy. Over time, the bacterial population can evolve. Outline the theory of evolution by natural selection. Right, this is quite a tricky one. So evolution by natural selection goes like this. You could have a population, let's say these bacteria are all just living here. And as they reproduce, you get a mutation. One of them will be slightly different from the other. And if this mutation is useful, let's say that this guy mutates somehow and he makes a certain protein that's going to be useful to him. Well, it's not him, it's bacteria, so that person. If this is useful, this mutation is useful, this bacteria will survive more and reproduce more. And all the offspring of this bacteria will also have whatever this mutation was. So the mutation becomes more and more common as it splits and splits and splits. So this means that the mutation, if it's useful, will help the bacteria to survive and reproduce. So it'll be more prevalent in the species. So just to recap, you get through mutations. I'll just kind of use bullet points for this, okay? Mutations happen during reproduction. Some of these mutations are going to be very bad and will be no good, and that thing will just die, but some of them will be useful. Some mutations are useful, or helpful, whichever you want to say. And if they're helpful, they'll help the organism to survive and do better. So to survive, and very importantly, and reproduce. So that when this reproduction happens, it will lead to this useful mutation becoming more common. Okay, and that's evolution by natural selection. Just to break down the words, evolution just means a change, and natural selection is how nature selects that this thing is useful, this thing isn't. And it's just by, if it's useful, you'll survive and reproduce more, and if it's not, you won't. That's it. Simple as. Okay, let's keep cracking on. Question 13. Mad looking thing. What have we got here? The periodic table was developed by Dmitry Mendeleev. It was published 150 years ago in 1869. To celebrate the International Year of the Periodic Table, the European Chemical Society has designed a new kind of periodic table called the 90 elements that make up everything. Now we are over here. So it's color coded. We have in red elements of which the availability is seriously threatened in the next 100 years. Orange means there's a rising threat to the availability. This light green means limited available future risk to supply. Green means there's a plentiful supply, and if it's got a white symbol of a phone on it, it's elements that are used in the making of a smartphone. Okay, the table has been drawn so that the area occupied by each element indicates how much of that element is in the Earth's crust and atmosphere. Okay, so think about the Earth. You've got the crust is just a thin layer around the outside, and the atmosphere is an even thinner layer of gases. Most of the core and mantle we're not talking about here. We're just talking about in the outer levels that we can get access to. From the table, and the bigger the area, the more we have of it. So we've got loads of oxygen, but we don't have very much lead. Okay, I couldn't remember what that fella is, to be honest. Is it HI? I can't make it out. Okay, from the table below, or above, identify a gas which is a component of the Earth's atmosphere and which is in plentiful supply. Okay, if you think about the Earth's atmosphere, you've got nitrogen, you've got oxygen, carbon dioxide, argon and other stuff, but it's mostly nitrogen, 78% nitrogen, 21% oxygen. So let's look for what we've got here. We've got, either nitrogen or oxygen are both good answers here. We've got plenty of them. So let's go with oxygen, which is useful for us because we need it to stay alive. Why should the use of the gas helium in birthday balloons be avoided? Okay, well, helium is this little red squiggle up here. And I'd say it's because we don't have very much of it, and our availability is threatened in the next 100 years. So we need to use it for things more serious and important than birthday balloons. It's kind of anti-crack, as that sounds. So why should the use of gas helium in birthday balloons be avoided? Availability is threatened. And we don't have much. The element indium, IN, is used in smartphones. At current usage rates, indium will be used up in 50 years. Suggest one way humans could contribute to sustaining levels of this element for future generations, perhaps by making less smartphones or recycling smartphones that we already have. So, in fact, that's reducing the amount that we make, reusing the ones that we have, or recycling the element from old mobile phones that maybe don't work anymore. So reducing it, reusing it, or recycling it. I'm kind of speeding things up a bit here, guys, because I want this to take ages. People will be drifting off as we go. Now we're getting there. In fact, we've only got one question after this. Let's keep cracking on. Let's just blitz it. The diagrams on the right show the arrangement of particles in the elements aluminium and chlorine at room temperature. What evidence is there in the diagrams to support the classification of these substances as elements? Okay, what they're asking here is to make sure you know what an element is. And an element is when you've only got one of that particular type of atom. So, for example, oxygen would be an element. Even though it's made up of two atoms, they're both the same kind, they're both oxygen. Whereas water, H2O, which is made up of hydrogen and oxygen atoms, that's not an element, that's a compound because it's got two different types of atom inside. So the evidence that in the diagrams that these are elements, each one is the same color. So each one is only made up of one type of atom. Each one is only made up of one type of atom. So in the aluminium, there's loads of them, quite close together because it's a solid. In the chlorine, two of them pair up and they're quite spaced out from each other because it exists as gas. Which of these elements is a solid at room? I just think I just answered this. Which of these elements is a solid at room temperature? Well, it's aluminium. And justify your answer. Well, from the diagram, because that's all we really have to go on. You might just think of aluminium as being solid anyway at room temperature, but the evidence from the diagram here is the particles, if you look at how they're arranged, are closely packed together. So that could mean though that it's either a liquid or a solid, but they're closely packed and they're in a regular arrangement. They're all lined up like 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Closely packed and regularly aligned, I suppose. I don't know how you could say that in a load of different ways. Aluminium reacts with chlorine to form the compound aluminium chloride. Use the periodic table on page 79 of the Formulae and Tables book to predict the ratio of aluminium to chlorine in this compound. Hence, write the chemical formula for aluminium chloride. Or I wish I'd got the Formulae and Tables in front of me. So let's see if I can do this on my tab. So we've got aluminium and we've got chlorine. Now I think, and you'll have to bear with me guys for a second, I think aluminium's in group 3. Chlorine is in group 7, right? Go right to your textbook here. Let's go right to the back. Yeah, aluminium's in group 3 and chlorine is in group 7. Group 3 and group 7. Now, this is where you have to think about where the electrons are. So this means that aluminium has got 3 electrons in its outer shell. So if I was to draw aluminium, it would have 1, 2, 3 electrons in its outer shell. Whereas chlorine has got 7. 1, 2, 3, 4, 5, 6, 7. So chlorine needs to get 1 extra electron from somewhere. Okay. Let me just make sure I want to make sure I'm not making some silly mistake here, guys. So aluminium, just going to run through this in my head, has 13 electrons, so it's got 2 in the first shell, 8 in the next, and then 3 in the next. So I think each aluminium atom, if I'm getting this right, needs to get 5 extra electrons from somewhere to fill in this, to get a full outer shell. Whereas chlorine needs to get 1 extra electron from somewhere. So I think that for every aluminium, you're going to need 5 chlorines. Just make sure this makes sense in my brain. Yeah, I think that's right. Now I need to double check that, guys, because my brain is mush. I think I'm pretty confident AlCl5. So the ratio of aluminium to chlorine is 1 to 5. Now if I made some silly mistake, which is quite possible, I'll clear it up later, but for now, I'm going to stand by that. Aluminium in group 3 needs to gain 5 electrons. Chlorine needs to gain 1. So you need 5 chlorines for every aluminium. So you'd have like an aluminium, and then you'd have 1, 2, 3, 4, 5 chlorines, like covalently bonded. Alright, definitely getting trickier now. Elements can be classified as metals or non-metals. The table shows some of the properties of 3 elements from the periodic table. Element 1, element 2, and element 3. Which element, 1, 2, or 3, is most likely to be a metal? Justify your answer. Okay, I'd say it's probably element 1, because it's a conductor of electricity. It melts at a very high temperature, which is what most metals are like. Whereas element 2 and element 3, it would melt at like -7 Celsius. So at room temperature, it would be a liquid or a gas, depending on. So element, well, that's probably going to be a next question. In fact, it is. Let's leave that for a moment. So it's element 1. And you could say high melting point or boiling point, both good observations, and also conductor of electricity. Any of those would have done the job. Which element 1, 2, or 3 is a liquid at room temperature, which is 20 degrees Celsius? Justify your answer. Okay, well, element 1 will be a solid because it will only melt at 1538 degrees Celsius. Most rooms are 20. It's not enough heat to melt element 1. Let's look at element 2. Element 2 would have melted at -7, and it hasn't yet boiled. So I think it's element 2. And just to complete it, before we come back to finishing the answer, element 3 would have melted at -101 degrees Celsius, but it would also have boiled way before it reached room temperature. It would have boiled at -34, so it's a gas at room temperature. So element 2, because 20 degrees Celsius is in between its melting point and its boiling point. If I was to plot in a graph, -7 will be over there, 15 will be over here, and 20 will be in the middle. So room temperature is in between its melting and boiling points. Okay, we're getting there. I think there's only one question to go, guys. So if you're still with me, fair play. Now remember, of course, during all this, take a break if you need to. Okay, keeping focused like this for such a long time is tricky. All right, that being said, I think this is the last question, is it? Yeah, okay, let's do it. Okay, 2019 marks, this is question 16. 2019 marks the 50th anniversary of man's first landing on the moon. Since then, there have been a number of other missions to the moon. The diagram below shows the Earth orbiting the Sun. Complete the diagram to show the shape, location, and motion of the moon in the Earth-Sun-Moon system. Okay, let's start with what we know. The moon goes around the Earth, okay? So its path is going to be like that. It doesn't go flying off and go around the sun or anything. It just goes around the Earth. And so that's its location, the shape. It's kind of spherical. And motion, going around in a circle around the Earth. There we go. I don't know how many marks it is, but boom. At the time of the first moon landing, the moon was in waxing crescent phase as seen from the Earth. The images below show different phases of the moon in sequence from left to right. Place a tick in the box below which shows the moon in a waxing crescent phase. And it's this fella here. First off, the crescent is that shape there, like a crescent moon, that's what it means. Like that kind of shape, like a banana. Boom, Bob's your uncle. Shading the image of the moon on the left to illustrate the next phase of the moon in the sequence above. Okay, let's think about what's happening here. The moon is going around the Earth, and it's from the position of an observer as you look at it. If the Earth is in the way of the sun, you wouldn't see the moon. It's just, you don't see it. If the moon was, it's because it's kind of dark. If though it's, did I just make a stupid mistake? Let's think it through. All right, so the moon's going around the Earth. If it's just going above during the day, you wouldn't see it because it's, well, you see it, but it's kind of small, it's in the background. The only time you'd be really noticeable is if it casts a shadow directly on the spot you're walking on, and that's called an eclipse, when the sun's being blocked out by the moon, solar eclipse. So it's going around, and as it goes around, you see, the way to think about it is how much of the sun is reaching the surface of the moon. So here, you're getting like more and more it's kind of shifting that way. So in fact, I think the next thing, this is a full moon where you can see it fully. The next one is this side. I see it's going. Yeah, I think that you're going to get kind of this bit will be darkened. See less of it. Because like, if you think of it as you're going left to right, you're getting more and more of the sun hitting the surface of the moon, from our perspective. But then when you reach here, it's full moon. It's actually going to keep going in that direction. It's very hard to explain over this. I think in person we'll be able to explain this much better. That's how I normally teach this. Okay, so blah blah blah. On January 22nd, 2019, the Chinese Chang'e 4 lander touched down on the far side or dark side of the moon. Explain why this side of the moon is never visible from Earth. Okay, well, here's the thing. This is kind of a strange one. Even though the moon goes around the Earth, it doesn't spin itself. It just goes around. So from our perspective, we only ever see one side of the moon. The other half is always pointed away from us. Because we call it's tidally locked. It just means that the other half of the moon we never see. It's in the dark the whole time. That's what we mean by the dark side of the moon. So explain why the dark side of the moon is never visible from the Earth. Well, the dark side always faces away from the Earth. Not so great help. Always faces away from the Earth. So just to be clear on the difference, the moon goes around, but it doesn't spin. I wish, do I have a couple of coins? I don't. But imagine it this way. Just for a moment, imagine that that's the Earth, right? And this is the moon. It goes around, but this bit is always facing inward. It doesn't spin like this, like the Earth does. Very confusing to picture in your brain until we're doing it in person. Okay, the dark circles visible on the moon's surface are craters. Craters occur when objects with high speed strike the surface of the moon. Examples of such objects are asteroids and comets. Okay, an asteroid is a big rock in space. Big rock in space. That has to be the least sciencey answer I think I've ever given. Yeah. Okay, where are we at? So we got a graph one. Just go ahead here. So we got big rock in space. That doesn't seem like the best answer possible, but what it is. Like an asteroid is just a big rock. Comets are mostly ice. So yeah, big rock in space, traveling fast. All right. Many investigations were carried out during missions to the moon. One investigation measured the temperature of the lunar surface at various depths. So as you go deeper down, what effects does the temperature have? The graph shows the temperatures measured at different depths over a period of time. So time in Earth days, temperature in K for Kelvin, that's just like another measurement for temperature. 30 centimeters below the surface, 15 below the surface, and the surface. Okay, describe how the temperature on the surface of the moon, the red line, changed with time. Suggest explanation for this pattern. Well, how it changed with time is first it increases, and then it increases, and then it increases again, and then it decreases again, then it increases again, etc., etc. And the full cycle to go from the same point of the graph to the same point, like say from the top to the top or the bottom to the bottom, well, we start off at 0, and the next time it reaches this point where it's at the bottom and going up, so it's gone up, it's gone down, it's gone up, is here, which is about 30 days. It's actually 28 to be exact, but it's about 30 days. So describe how the temperature on the surface of the moon, red line, changes with time. It increases for 15 days and then decreases for 15 days, then increases for 15 days, decreases. Suggests an explanation. Okay, the explanation is that as the moon goes around the Earth, it takes 28 days to do this. It's called a lunar orbit. And in fact, 28 days. If you think of the word month, that actually comes from this. It comes to the fact that think of like the moon, if that helps. It takes 28 days for the moon to go around the sun. Sorry, around the sun. That was a stupid mistake. It takes 28 days for the moon to go around the Earth. The moon does not go around the sun. So that's what causes this increase. At different points, it will be fully exposed to the sun. So let's recap here. At this point here where the temperature is highest, that's when the moon is in this position and it's getting the most energy from the sun. When it's lowest, it's when it's away from the sun with the Earth in between, so it's getting less heat from the sun. That's why its temperature's gone down by so much. Okay, describe the relationship between the depth below the surface of the moon and the change in temperature and suggest a reason for this. Okay, so surface, this is going a little bit deeper and then very deep. But let's look at the very deep thing. If you go 30 centimeters below the surface, the temperature is the same because it's kind of buried underground. When you're going 15 centimeters below the surface, quite near the surface, you do get this fluctuation, just like before with the surface, but it's less pronounced because it's not much of the heat isn't quite reaching there. So as you go deeper down, less and less of the sun's heat is reaching the soil. Not soil, because it's the moon, but the rock. Okay. That was trickier than I thought actually. I almost made a stupid mistake there. Remember, the moon goes around the Earth and not the sun. Alright, the diagram shows the mass and weight of 4 objects, A, B, C, and D on the Earth. Earth's moon, Jupiter, and Venus. So this is on the Earth, this is on Earth's moon, Jupiter, and Venus. Okay, so they've got different masses and different weights. Which object A, B, C, or D has the smallest mass? So mass is measured in kilograms, and the object, C, has the smallest mass in kilograms, so C. How can you tell that the force of gravity is less on Venus than it is on Earth? Okay, well if you compare these two, they're both the same mass, 8 kilograms, but on Earth it's pulled down with a force of 80 newtons. On Venus it's only pulled down with a force of 72. So the same mass is pulled with less force by Venus's gravity than Earth's. Okay, and just to be clear on this, the difference, mass is just how much stuff you have, weight is how much the gravity will pull you with, and depending on where you are, that will be greater or less. So for example, if you look at Jupiter, right, even though only a kilogram of mass in Jupiter is pulled with a force of 25 newtons, it's got crazy high gravity, whereas on Earth, each kilogram is only pulled with a force of about 10 newtons. So on Jupiter, the gravity is much stronger than it is on Earth. Okay. So, during the Apollo 15 mission to the moon in 1971, astronaut David Scott conducted the famous hammer and feather experiment. He dropped the hammer and feather at the same time, from the same height, and they hit the surface of the moon at the same time. On the Earth, however, a hammer travels much faster as it falls than it does on the moon. So why does this happen? Well, the reason this experiment worked in space, and the reason why it was predicted by Galileo Galilei, is that on the moon, there's no air. There's no air to slow down the objects. There's no air resistance. So it doesn't matter what the objects are, they're pulled they're accelerated by the same amount by gravity. So the short answer is, on Earth, air resistance slows the feather down more than the hammer. And boom, I think, is that the last question? Yeah, we're done. Alright guys, I hope that was helpful. Let me see if I can deactivate this. If you got any questions, any wobbly bits, don't be afraid to ask. And just to reiterate, I made a stupid mistake there, but it's just because I was talking offhand. Just to recap, the moon goes around the Earth goes around the sun, but the moon doesn't just fly off on its own and go around the sun. So it's like this delicate balance. As the Earth is moving around, the moon is moving around the Earth, and the whole shebang is going around the sun, which itself is moving in the galaxy. Alright, we'll talk to you soon, guys. I'm going to leave it there because my brain is mush because I'm making more silly mistakes as I go on. Alright, we'll talk soon.